Okay, what I want to do here is point out the familiarity of some of the parts of this. So if you saw this, if you saw that phrase right there, like everything, the other stuff, you just didn't even read, would that red highlighted phrase, would that not be coming from like September of when the veterans had AB? Like, in other words, that's something you've done a ton of, right? Write the equation of the tangent line. Write the equation. I mean, you heard that so many times last year, veterans. You probably dreamed about it, right? And you're like, oh, what a terrible dream. Maybe it was a good dream. I don't know. Whatever your perspective was. And so I just want to point out that this concept is something you've done a lot of. And even if all you did was count what our two new folks, Jaden and Jeff, have done, we have done that a lot already this year. We've done this a ton. Where this is different, of course, is how the function is defined. This is defined as a parametric function as opposed to y being in terms of x. That's what makes this a little bit different. And so we just encourage you to take your time and remember this. What are the two things you have to write the equation of a tangent line? Slope of tangent line and point of tangency. Yep, slope and a point. And so you're going to need those two things. And let me remind you one more thing before I just let you give this a shot. The slope of the tangent line, regardless of whether you have r's, t's, thetas, whatever, so the slope of the tangent line is always dy dx. And a point on the Cartesian plane is always x comma y. It's always the x-axis, always the y-axis. It's always going to be x comma y for the point. So you can find the dy dx for this, and you can find the x comma y for this. Bless you. Putting it together should be relatively straightforward. Why don't you guys give this one a shot? Go ahead and tackle the slope of the tangent line first. So the slope of the tangent line, given a parametric function, dy dx will equal dy dt divided by dx dt. And so in this case, dy dt would be 3 cosine of t, and dx dt would be negative 4 sine of t. So that would be your dy dx for any t value. And then, of course, we're looking for dy dx at t equals 3 pi over 4. So this is where the unit circle comes into play. It's a pi over 4 angle, and so you know it's going to be like a root 2 over 2 or a negative root 2 over 2. So 3 cosine of 3 pi over 4. We're in the second quadrant, so I think that's going to be negative, right? So it'd be negative 3 root 2 over 2 for the top. And then sine of 3 pi over 4, second quadrant, sine is positive, so it would be negative 4 root 2 over 2. And so, of course, what you see here is the root 2 over 2's cancel out, right? So we just end up with positive 3/4 for a slope of the tangent line. And then the only thing you got to have now is the point. And so the point, you could say something like when t equals 3 pi over 4, the point of tangency would be, negative 4 root 2 over 2? Comma 3 root 2 over 2. Where I'm getting that from is I'm just plugging 3 pi over 4 in for the t value in both of my x equals and y equals, right? Okay, so then final step here is just put it together. As you know, I favor point slope, and so I'm just going to write y minus the y coordinate equals slope times x minus the x coordinate. And of course, there's a little simplifying. You could have canceled the 4 with the 2, and you could say minus a negative is really plus a positive, and whatever. I'll leave that up to you. What do you guys think? Questions? You see how it's all the same elements, just different ways of getting to those same elements? Yeah, Brandon. Say again?
Wait, for just like grading in general, is
Sure.
there a point for showing like the dy dt over dx dt? Or
So in other words, do you have to write this down?
yeah.
No. In fact, I would say Yeah, I mean, I trying to think this through points wise, and like if you, like let's say you wrote this for your slope of the tangent line. Let's say you just wrote dy dx at t equals 3 pi over 4 equals 3 cosine of 3 pi over 4 over negative 4 sine of 3 pi over 4 equals 3/4. Like if that's all you wrote, to me that communicates it pretty well. Like the idea here would be, like with showing your work, really, honestly, the idea would be trying to communicate to me that you know how to get to where you needed to go. And so I'd say like what I wrote up there would be a minimal sort of thing. I would encourage you not just to write, hey, dy dx t equals 3 pi over 4 equals just 3/4, because if you mess it up and write 4/3, I'm not going to assume and just be like, oh man, they just vertically flipped it or whatever. If there's no work shown, I got to just be like, I have no idea. You'd be surprised how many times over the years, like I've graded somebody's quiz and I've marked it, they missed it and I marked it with whatever I did. And in my mind, I thought to myself, oh, I know exactly what they did wrong. And then I hand it back to them, and I'm like chatting with them. I'm like, oh man, I can't believe, you made this mistake. And they're like, that's not how I was thinking about it at all. I was like, oh. So I can't assume that like you almost had it. By the same token, I can't assume that you were like way off either. The only way for me to know and the only way for you to communicate is to show me a step or two. So, I don't think that that's necessary. I think the other ones would be helpful. Something like that. Anyway, okay. Anybody else? Question? Colin, you look like you were processing something. Did you figure out whatever? Okay. All right, awesome. So if you haven't already looked at number 3, please do. Number 3 is similar kind of a question, but it asks certainly for a different result. Find all, and I will say, I know on quizzes and tests when I ask questions along these lines, I'm usually really, really clear about this. This one is like sort of clear. It says find all points of horizontal and vertical tangency, given those equations. Somebody could say, are you talking about a point in time? Are you talking about a t-value, or are you talking about a point on the Cartesian plane, right? It's a little ambiguous. I would say for us here, let's go ahead and get to the Cartesian plane points. You gotta have to have the t to be able to get to the Cartesian plane points. So let's go to the x comma y for this one. So you guys okay with getting started? Again, let me put it in this perspective. Again, I am hoping that when you see this kind of phrase, find all points of horizontal and vertical tangency, that immediately brings to mind a concept. You're like, oh, that's where blah, blah, blah. That's where whatever. Of course, these are presented differently. These are presented as parametric as opposed to y in terms of x. But I'm hoping that the red phrase looks really familiar, and then maybe you could adapt the parametric stuff to what you already know. So give it a try. From this discussion. So here it is. You all know, you're getting more familiar with this, of course. dy dx is dy dt over dx dt. And then here's how you decide the t values and ultimately the x and the y values for where you've got vertical or horizontal tangent lines. So I'll just write it out like this. Horizontal tangent lines happen when dy dt equals 0 and dx dt doesn't equal 0. So horizontal tangent lines happen when dy dt is 0, but dx dt isn't 0. And then, of course, vertical, I'm sure you can imagine, is similar. Vertical tangent lines will happen when dx dt is 0 and dy dt isn't. So there will be times, literally, there will be times when dx dt and dy dt are both 0, and in cases like that, we're going to say that there is no tangent line. It's going to be the proverbial, probably a sharp point. You'll see that come up from time to time. So that's why we put that in there. In that case, of course, the tangent line would be neither vertical nor horizontal, just there wouldn't be one because the slope wouldn't exist. Okay, so armed with that idea, if I'm going to be looking for horizontal, I'm going to start off by setting dy dt equal to 0. So dy dt equals 2t minus 3. And just a reminder that if you are going to be setting something equal to 0, don't just set it equal to 0 in your head, write it down, right? Because if you don't actually write equal 0, there's really, honestly, there's nothing to solve. Does that make sense? But if you write down equals 0, now there's something, and of course for you guys it's very easy to solve. So here you get t equals 3/2. So we're going to provisionally say that's probably when the time we have a horizontal tangent line. We've got to double check what's going on with dx dt. So I'm going to say for my vertical tangent line, dx dt, which is 2t plus 1 equals 0. And so t equals -1/2. And that's the only place where dx dt is 0. And of course, that's different than t equals 3/2. So the whole, you can't have dy dt and dx dt equal to 0 at the same time. It's not going to play into this one, right? Does that make sense? Okay. So then the way we finish this one off is simply to say that we have a horizontal tangent line at, and now we're going to give the x, y coordinates for this. So we just need to plug in a 3/2 into both. So it's what, 9/4 plus 3/2, so 15/4. So 15/4, comma, and then 9/4 minus 9/2 would be -9/4 plus 20/4, 11/4.
Wow.
All right. Fraction addition. We can do it. Okay, does that make sense? All right, and then the other one, of course, t equals -1/2. So we're going to say we have a vertical tangent line at, and then we do the same thing. We plug in the -1/2 in for the t values in both x and y. So it's 1/4 plus -1/2, so -1/4, comma, the y 1/4 plus 6/4 is 7/4, 27/4? Yes? Okay. Okay, so there you go. There's your 2 points. And if you wanted to, and I think it would be worth your while, you could take this parametric equation, these 2 parametric equations, and graph them and look for those 2 points. But maybe take a minute and do that. Plug them into your calculator and look for the vertical tangent line point and the horizontal tangent line point and see if they match. See if it all kind of makes sense that that's where these features would be. Hey, makes sense on the graph? Can you see it?
I don't think I did it.
If you're having issues with the graph, maybe something to think about is to go into your window. I'll show you. I'll check it out myself here. Parametric mode. So t squared plus t squared minus 3t plus 5. So I just put it in there. If I hit graph, yeah, I can see how someone would look at this. Maybe this is what you had on your graph. Can you see how somebody would look at this and say, right here, this seems like a pretty clear horizontal tangent line. Right about there. Pardon the poor execution of the line. Do you see it? Did you see how somebody would be like, well, yeah, but where's the vertical? I don't see any vertical tangent lines in there. What do I need to do? Change my window. Yep. So if I go into window and I know that, come on, window. There we go. So if I go to the window, oh, that's why. Look at that. So the reason why I can't see the vertical tangent line is the vertical tangent line happens when t equals -1/2, and notice that my low t value is 0. So if I go in there and I say, you know what, I want my t min to be like -5, and I don't really need 60 there. That's what was taking so long. Maybe something like that. Perhaps now that I've reset my t values, there we go. You can see the vertical tangent line showing up over there on the left because I actually put the time when the vertical tangent line happens into my domain. And so maybe you can see the domain here will really matter. There's my vertical tangent line. There's my horizontal tangent line right about there. So if you can't see something on a parametric graph, go back and look at your t min and max. That might be the reason that you can't see the thing that you thought you were going to see. Just readjust to the appropriate values. Okay. So if you haven't already looked at number 4, please do. So the length of a curve in parametric form. So we've looked at arc length before. We looked at it in non-parametric form. That would be your formula. Hopefully you can see the distance formula played out there again as well. So if you would, please try number 4. Set up an integral expression for the arc length of the curve given by those parametric equations. So number 4, keep in mind with an integral, with a definite integral, at least for us in single variable calculus, the differential, which is the dx or the dy or the dt or whatever that little expression is on the end, that's what really sets all your variables up to be what they're supposed to be. So if we are going to be doing this in parametric form, we got this dt right here. That means everything within your integrand has to be in terms of t, including the limits. So then when you look at this, set up an integral expression for the arc length, you'd say, all right, arc length equals the integral from, it might be tempting to look at these two domain values and say, all right, 0 and 1, we need to turn those into x's or we need to turn those into y's. But the truth is, they're already t's. And because it's a dt is a differential here, we want to leave them in terms of time. And so this would be one of those situations where you could easily talk yourself into doing the wrong thing. Hey, they're always x's, or I think maybe these are y's this time. No, everything needs to match. That principle has not changed. Okay, so integral from 0 to 1, and then dx dt would be 2t. So 2t squared. Dy dt is 12t squared. And then squared dt. So that would be all it is. Questions? Okay. So then number 5, I'm going to let you guys do a little exploring with, but I want to make sure I point out one thing. Okay, so it says for those parametric equations on that interval, and then it says find the leftmost point. Can anyone reinterpret what it means to find the leftmost point? Say again? The lowest x value? What do you think? Lowest x value. What's another word for the lowest? Minimum, right? Same thing. So we're trying to find the lowest or the minimum x value on this interval. And so I'm hoping that when you think, oh, we're looking for the lowest, we're looking for the minimum on this interval, hopefully that's the part of this question that is really familiar. Like, oh, I found lots of lowest thises and that's, and lots of minimums of whatever. It's the same concept. Ready? Give it a shot. Listen carefully. As you start to try to, you do a few details, you do a few steps, but overall there needs to be a plan. I want you to listen very carefully to my question. Did you use, we're trying to find a minimum, right? Minimize x. Did you use the first derivative test or the second derivative test? I haven't heard a good answer yet. No, answer my, no. Did you use the first derivative test or the second derivative test? I have yet to hear the answer that I was hoping for.
Third derivative.
Oh, the third derivative. It's a new one. No, not the third. I'm betting that someone maybe has the right thought. They're just being really quiet. No.
All three.
Did you use the first or second derivative test? That's a way that we could find a certain type of minimum, right? Did you use the first or second derivative test?
Neither.
Neither is the right answer. Yes.
I didn't actually.
Why would you use neither?
I don't know.
It was a good answer, but now it sounds like a guess. Sounds like it was a guess.
It definitely was.
Why would you use neither?
Because you don't need to.
Because you just assume
You
that
don't
it's
need
right.
to. Yes, that's like kind of the square peg round hole thing. It doesn't fit for this one. And here's the key idea. We are not asked to find a relative minimum. The only thing the first or second derivative test will tell you, with some caveat in there, is relative minimums or relative maximums. Did you notice that this was on an interval? Did you notice the graph was on a closed interval?
Oh my god.
That means the endpoints of the graph matter. The endpoints could very well be the minimum, or in maybe in another case, the maximum. The endpoints will matter. So the first derivative test, where you say, hey, did the first derivative go from negative to positive or positive to negative? Really doesn't matter here. Second derivative test, hey, is second derivative positive or negative? Therefore, we have a relative min-or-max, whatever. Really doesn't matter. All we need to do is really figure out what's going on at the endpoints and what's going on at a specific type of critical number. We're good. So here's maybe what it could look like. I am trying to minimize or find the lowest x. And so the first thing I'm going to do is I'm going to find dx dt. And I'm going to set that equal to 0. Right? So I'm trying to minimize x. I'm not trying to minimize y. And frankly, bless you. Frankly, until the very end, I don't really care anything about y. I'll care at the very end. But right now, I don't care at all. I just want to know where is the rate of change of x, 0. That's going to give me a vertical tangent line, which would potentially be a leftmost point. Okay. So then, of course, this gives me t equals -1. And that is my lone interior candidate. My endpoints are -2 and 3. And so what I'm going to do is set up a little chart. I'm going to make a double t chart. I'm going to say my inputs are t's, and my outputs are x's, and eventually I'll consider the y's as well. Okay, so my t values would be -2, -1, and 3. I'm only going to concern myself with the x's right now because I'm looking for the leftmost point. This would be the minimum value of x. My candidates are endpoints and critical numbers because I'm on a closed interval here. So I'm just going to plug in the t values into my x equation. So if I plug in the -2, I get 4 minus 4. If I plug in the -1, I get 1 minus 2. If I plug in the 3, I get 9 plus 6. So then I look through that column and I identify the lowest x value, right? The lowest x value right here, -1. And so I'm going to find the y to go with that. So when t is -1, y is 1 plus 2 plus 3? 6. And so the leftmost point is -1 comma 6. And that's, of course, when t equals -1. Make sense? So really great connection back to some old AB stuff, right? Anyways, so maybe armed with that kind of information, perhaps number 6 will be a little bit easier for you. So if you would, please check out number 6. Make sure that you're using a good process there for finding the highest, right? Highest point. Try to interpret that into giving you a strategy about what to do. Trying to maximize y. And if I'm trying to maximize y, I'm going to set dy dt equal to 0. So dy dt equals -2 sine of 2t. and I'm going to set that equal to 0, right? Dividing by -2, I get this sine of 2t is equal to 0. Here's where I'm going to do the inverse sine of both sides, or make both sides the input for inverse sine. So the left side, the inverse sine cancels with the sine. You just end up with 2t. And then for what angle is sine 0? 0. But if you notice, 0 divided by 2 is going to be 0, and that's not in the domain. So we're going to have to hunt down some other values. So how about pi? 2 pi, 3 pi, comma, dot, dot, dot. Could keep going. You divide by 2, t equals 0, pi over 2, pi, 3 pi over 2, so on and so forth. Maybe we need to go further. Maybe we don't. Which of those values actually fits within the domain? Pi over 2 and pi. Is 3 pi over 2 a little bit too big?
4.6.
Just a little bit too big. Okay. It's almost like this question was designed. I know. So then I've got my t values. I've got my x's. I've got my y's. My t values would be 1.5, pi over 2, pi, and 4.5. I'm looking for the highest value, so I'm going to plug these into the y and hunt down the highest y value. Anybody have the table complete? When you plug in a 1.5, what do you get for a y? 0.999. Yes? Okay. When you plug in a pi over 2, you get cosine of pi, which is -1. You plug in a pi, you get cosine of 2 pi, which is 1. And then 4.5, when you plug that in, what do you get? -0.911. Okay.
Must be 1.5 be negative 0.9.
Yeah,
The first one's negative? Okay.
doesn't really matter though.
You're looking for the highest point, so isn't this our highest y? Right there. So you'd plug in the pi to get the x to go with that. So 2 sine of pi is 0. So you'd say the high point is 0, comma, 1. Okay. So I feel like there may be a few adjustments in thinking to be had there, but I feel like you're adapting well. Tomorrow we'll do a little bit of reviewing and starting to work our way into vectors, but that's it for parametric. Homework 2 hopefully will go well. Jasmine.
So for homework, we have to turn it in class tomorrow?
So homework shouldn't be due until Friday.
It said it was like Thursday. Yeah, Thursday 11:15.
Well, if I need to go back and change it, I'll change it. Should be. I just want you to have it done before your quiz, and your quiz should be Friday. So, anyway, yes, Jeff.
Homework on the website.
Homework is on. It's on Schoology, so it's paper-based homework, and so you'll just just turn in a packet. Yeah, the answers should be there, solutions and everything, so you can check yourself and see you're hopefully doing well.
So print it out.
Just print it out. Yep. Or if you want to do it electronically, like you have an iPad, you want to do it electronically and just email it to me, or post it to Schoology, you can do that too. Yeah, either way is fine. See you guys.
Thank you.
Have a great day. Thank you. It's recording right now.
Hi, Alex.
Hi, Alexandra.
I hope you're doing well and doing lots of dancing or whatever you're doing.
Keep up the good work. And have a Merry
fun.
Christmas. We'll see you maybe soon.
Merry Christmas.
Merry Christmas.
Mary Chrysler.
Done.
And